Hello there, and welcome back to the sleep science corner of the internet, where the cosmos stretches out like a velvet blanket and you, strangely enough, are tucked right inside it. Picture yourself floating in a darkness that isn't just absence, but a kind of weighty presence, thick with potential stories waiting to be whispered. Black holes sit out there, invisible yet monumental, like vaults stuffed with secrets they'll never voluntarily give back. You probably won't survive a personal encounter with one, unless your bucket list includes being stretched thinner than spaghetti, while time itself freezes you in place. But hey, at least you'll become part of the universe's permanent record. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And I'd love it if you posted in the comments where you're listening from and what time it is, because knowing someone in Tokyo is drifting off at sunrise while someone in Chicago is nodding out at midnight makes this whole experiment feel a little more like a shared dream. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You let yourself imagine black holes not as terrifying voids, but as giant cosmic filing cabinets. Every time a star, a planet, or even a lone particle crosses their threshold, it's as though the event is stamped into some invisible ledger. This is not just sci-fi fantasy. Real physicists have wrestled with this notion for decades, sometimes with chalk dust-covered blackboards, sometimes with billion-dollar telescopes. The idea that black holes could store the history of everything isn't just about where matter goes, it's about whether the universe keeps receipts. Think of the history of humanity. Every laugh, every sneeze, every half-finished text message, all radiating tiny bits of energy. On Earth, they disperse, fade, and vanish into the noise. But if some of that information eventually drifts toward a black hole, does it vanish completely, or does the hole keep it forever, buried under layers of warped space-time? Historians still argue whether Julius Caesar really said, "Et tu, brute?" Imagine if the definitive answer is locked in the archives of a distant black hole, preserved like a cosmic audio recording. The funny thing is, our species once thought the night sky was unchanging and eternal. Ancient Chinese astronomers dutifully recorded guess stars, what we now call supernovae, sometimes noting bright objects that faded after weeks. One such record from 1054 describes the explosion that birthed the Crab Nebula. Those same chroniclers had no clue that the wreckage of some collapsing stars would eventually become black holes, compact enough to trap even light. Meanwhile, here you are, lying in bed, letting your brain wrestle with the fact that the same cosmos that grew tea leaves and chopsticks also brews singularities. And then there's the fringe stuff, the kind you hear late at night when science conferences slip into the bar. Some theorists toy with the possibility that every black hole could encode an entire universe inside, like Russian nesting dolls of reality. That means you, right now, could be living inside the record of a black hole in some parent cosmos. If that's true, it's not so much bedtime science as bedtime existential crisis. But hey, at least it gives new meaning to the phrase "your whole life flashing before your eyes." You settle into this thought the way you'd settle under a heavy blanket. The darkness is not frightening but oddly reassuring, as though the universe has a backup system that refuses to lose track of you. Your mind drifts along questions. Does the black hole keep your molecular arrangement, your memories, or just a blurred statistical smear like a photocopy of a photocopy? No one can say for certain, and that's the real lullaby here. The cosmos hums with uncertainty, a gentle reminder that even the smartest humans don't know if our most intimate stories are vanishing or being etched into space-time forever. You watch the last glow of a massive star flicker, and you feel the sheer exhaustion of something that has been burning for millions of years. It's like a bonfire that's been raging all night, finally sputtering out as the logs collapse into ash. Except here, the logs are billions of tons of hydrogen and helium fusing into heavier elements. In your quiet mental theatre, the star swells into a red supergiant, wobbling like a balloon that's far too full. Then, almost without warning, the core implodes, and you realise you're witnessing the birth of a black hole. The drama is so immense that you almost forget this is standard stellar evolution. For stars much more massive than our own sun, the endgame is unavoidable. Gravity wins. Gravity doesn't argue, doesn't compromise. It just pulls and pulls until even the atoms themselves can't resist. The layers of the star collapse inward. crushing the core until electrons and protons fuse into neutrons. Sometimes that collapse halts at a neutron star, a city-sized ball so dense that a teaspoon of it would weigh as much as Mount Everest. But push just a little more, and even neutrons can't hold the line. That's when a black hole forms. Historically, the idea that stars could collapse into something so extreme was considered almost impolite. In the 18th century, John Michell, an English natural philosopher with a flair for unusual predictions, casually suggested the existence of dark stars, whose gravity would be strong enough to trap light. His peers found the notion amusing, perhaps a little too imaginative, like the cosmic equivalent of saying, "What if my horse could teleport?" It wasn't until the 20th century that Einstein's general relativity gave Michell's hunch some real teeth. And even then, Einstein himself wasn't thrilled about black holes. He thought nature would find a way to avoid such absurd extremes. Joke's on him. As you float through the collapse scene, you picture all the matter. Iron, silicon, carbon, sliding inward, layer upon layer, like a skyscraper pancaking into its own foundation. The star that once lit entire solar systems shrinks until it has no surface at all, just a gravitational pit so deep you can't see the bottom. You might think of it as tragic, but it's also a bit of cosmic recycling. The heavier elements forged in the star's belly get hurled out into space during the explosion phase, seeding future worlds. Your blood's iron atoms, very possibly forged in a star's collapse long ago. So the death of one sun might literally have written the preface to your bedtime story tonight. Then comes the quirky bit. In some speculative circles, people have mused about what would happen if smaller stars, like our own sun, somehow bypassed the neutron star stage and collapsed straight to black holes. Technically, the math says it shouldn't happen. Our sun just doesn't have the mass. But there are whispered fringe papers wondering if exotic mechanisms, like extra dimensions or dark matter interactions, could nudge even modest stars into collapse. If true, it means the universe could be littered with far more black holes than astronomers currently estimate, like cosmic potholes hidden in the dark. Historians still argue whether the first confirmed black hole, Cygnus X1, was discovered through sheer luck or clever persistence. In the 1960s and 70s, astronomers were following mysterious X-ray sources puzzling over their cause. Eventually they realised that Cygnus X1's X-ray glow came from matter being shredded and heated as it spiraled into something invisible but massive. A bet was even placed. Physicist Stephen Hawking famously wagered that it wasn't a black hole. He later conceded, with his trademark humour, that losing the bet to colleague Kip Thorne was one of the few times he was happy to be wrong. You can almost smell the burned edges of the collapsing star if such a thing had a smell. Maybe something like iron and ozone mixed with the silence of deep space. It's a sensory illusion, of course, but your brain fills in the blanks. The collapse is violent but also graceful, like a cosmic dance that always ends with the same bow, a singularity cloaked in mystery. The thought is both terrifying and comforting. Terrifying because everything we know about physics seems to break here, comforting because it suggests the universe still holds surprises. You let that surprise settle into you, like a drowsy weight pressing against your chest. If stars can collapse so spectacularly, then maybe your own worries, the emails you didn't answer, the laundry waiting for you, don't matter quite as much. After all, compared to a supernova, your undone to-do list is pretty small potatoes, and in the end, both the potatoes and you are made of stardust anyway. You hover at the edge of something that has no edge, a place that looks ordinary until you try to leave. This is the event horizon, the black hole's one-way door. On one side, you're still in the universe, free to check your messages or binge another season of that show you pretend you don't watch. On the other, you're gone forever, stitched into the fabric of the whole. And the strangest part, to an outside observer, it looks as though you never quite cross. You just hang there, frozen in time, your light stretching redder and redder until it fades away. The event horizon is deceptively simple. The distance from the singularity where escape velocity equals the speed of light. If you were reckless enough to strap on a jetpack, it wouldn't matter how much thrust you had. Once you're inside, you're not leaving. The whole concept dates back to Carl Schwarzschild in 1916, when he solved Einstein's field equations for a simple, spherical black hole. The radius of that horizon, today called the Schwarzschild radius, can be calculated for any mass. For Earth, it's only about 9 millimeters, which means if you crushed our planet to the size of a peanut, voila, we'd have a black hole. Not the worst diet plan, yet the horizon isn't a physical surface. If you reached out a hand, there'd be no wall to touch, no dramatic boundary. You'd simply notice that all possible paths forward now tilt inward. Imagine walking down a mountain trail when suddenly the slope grows so steep that every step pulls you toward the valley, no matter how hard you try to climb back up. That valley is the singularity, and the trailhead you just passed without noticing. That's the event horizon. History drops another breadcrumb here. In the early days, physicists didn't call it an event horizon, they referred to it as a point of no return. The phrase sounds like something you'd find on a roller coaster sign. Beyond this line, no refunds. But it captured the essence. Only later, in the mid-20th century, did John Wheeler popularise the term black hole, giving the horizon its now familiar place in science and pop culture. And then comes the quirky twist. Some theorists have suggested the horizon might not be smooth at all. One fringe idea is that it could act like a cosmic hologram, encoding the information of everything that falls in across its surface. Imagine a USB drive with infinite capacity, except instead of a plastic stick, it's a shimmering sphere of nothingness. If that's true, then every particle you shed as you cross, every atom of your body, every embarrassing memory gets smeared into the horizon like jam on cosmic toast. A little messy, sure, but secure. Historians still argue whether falling through an event horizon would feel dramatic or anticlimactic. From your perspective, local physics says you should drift through without fanfare, because nothing unusual happens at that precise coordinate. Yet to an outside observer, you're burning and freezing and stretching forever at the edge. Which story is true? Both, depending on where you stand. And here's the kicker. You can't compare notes afterward, because once you're in, you're not sending postcards back out. You let your imagination linger on the horizon itself. You picture it glowing faintly, like the surface of a soap bubble in starlight, fragile yet absolute. You reach toward it, knowing you can't feel it, but you sense its inevitability, like the way sleep pulls you under at the end of a long day. A part of you resists, clinging to the comfort of the universe outside. Another part surrenders, curious about what lies beyond the curtain. And in this drowsy state, you recognize the comedy hidden in tragedy. The event horizon is like a cosmic velvet rope. On one side, the VIP lounge of reality. On the other, the mysterious after-party nobody talks about because, well, nobody comes back. You, of course, are standing in line, ticket in hand, wondering if your shoes are dress code compliant. You step closer, and gravity grabs you like an overeager dance partner, pulling you into a twirl you didn't agree to. Your feet, nearest to the black hole, feel the tug first. Then your legs, your chest, your arms. Each part of you is pulled with slightly different strength. The result? You start to stretch, slowly at first, then faster, like taffy warmed in the sun. The official term is tidal forces, but the less dignified nickname is spaghettification. You become a noodle of yourself, a cosmic linguine sliding toward eternity. It's absurd, it's terrifying, and yes, it's just a little funny, because who wouldn't want to be remembered as intergalactic pasta? In everyday life, tidal forces are gentle. They're why the moon makes our oceans bulge twice a day, sloshing water back and forth like soup in a tilted bowl. But near a black hole, those differences in gravitational pull ramp up to unimaginable levels. For a small black hole, the gradient is so steep that you'd be torn apart long before you even reach the horizon. For a supermassive black hole, though, things get oddly peaceful. The difference in pull across your body might be small enough that you could cross the horizon intact, at least for a while. It's cosmic irony. The bigger the beast, the gentler the bite. Back in the 18th century, French scientist Pierre-Simon Laplace mused about stars so dense that light could not escape. His calculations suggested such an object might exist, though the idea was shelved for lack of evidence. Historians still argue whether Laplace took his own proposal seriously or just tossed it into his book as a mathematical curiosity. Fast forward 2 centuries, and that throwaway speculation became the foundation for one of the universe's strangest jokes. You stretching into oblivion, while your shadow freezes at the horizon forever. And then there's the fringe detail. Some theorists argue that spaghettification might not be the end. Instead of shredding into atoms, maybe your information, every quantum detail of you, gets preserved in some weirdly ordered way. Imagine being stretched into a flat cosmic pancake, only to find that Pancake acts like a high-density filing system. It's not survival in any normal sense, but hey, you'd be organised. You hover in this paradox, both shredded and stored, both falling and frozen. To anyone watching from outside, you appear to slow down as you approach the horizon, never quite slipping in. They'd see your image fading and reddening, stretched across eternity like a cosmic Instagram filter gone wrong. Meanwhile, from your perspective, time flows normally. You don't feel frozen, you just keep falling. It's a two-perspective story, each true, yet incompatible. Which version is the real one? Historians and physicists alike still argue, as though debating whether Schrödinger's cat is napping or deceased. Your senses blur in the mental experiment. You hear nothing, because sound can't carry here. You feel no air, because vacuum is emptiness. All you notice is the unstoppable stretch, the sense that the universe has chosen a single direction for you. Forward, inward, down. It's oddly hypnotic, like the pull of sleep. You almost want to surrender, just to see how far the thread of you will unwind. And because your mind can't resist a joke at its own expense, you imagine a restaurant menu floating beside you. Special today, spaghetti a la human, served with a side of paradox and a sprinkle of Hawking radiation. Maybe the black hole is the universe's chef, and you are simply the latest dish. Grim, sure, but you can't deny it has a certain flavour of inevitability. You float deeper now, and the darkness takes on a mathematical texture, as though the universe has switched from painting with stars to scribbling equations across the void. The name that hums here is Karl Schwarzschild, a German physicist who, in 1916, solved Einstein's freshly minted field equations while stationed on the front lines of World War I. Picture it, artillery fire echoing, mud thick under his boots, and in his downtime he's casually cracking one of the hardest problems in theoretical physics. You may not be able to multitask laundry and emails, but Schwarzschild multitasked physics and trench warfare. That's the kind of overachiever who gives the rest of us an inferiority complex. His solution described the simplest kind of black hole, a perfectly spherical, non-rotating, uncharged object. No frills, no extras, just mass compressed so tightly that space and time curve into a pit. The boundary of this pit, as you already drifted past in your mind, is the event horizon. The distance to that boundary depends only on the mass. Double the mass, double the radius. It's simple, clean, elegant. Almost too elegant, which is why for decades many dismissed it as a curious artifact of the math, rather than a real possibility in the universe. The weird thing? Schwarzschild himself didn't live long enough to see how revolutionary his work would become. He died of illness just months after sending his solution to Einstein. Historians still argue whether Einstein fully appreciated the significance of what Schwarzschild had given him, or whether he quietly filed it under neat but impractical. Either way, the equation sat waiting, like a secret seed that would later grow into the towering oak of modern astrophysics. In this thoughtscape, you picture the Schwarzschild black hole as a flawless black marble hanging in space. No spin, no electric drama, no hair, as later physicists would quip. Just a silent sphere that swallows everything. If you could orbit at a safe distance, you'd find its pull indistinguishable from any other object of the same mass. A black hole with the mass of Earth wouldn't tug you harder than Earth itself, unless you strayed too close. It's the proximity, not the weight, that gets you. And here comes the fringe speculation. Some researchers have toyed with the notion of mini black holes left over from the early universe, perhaps as small as a mountain, or even an atom. If Schwarzschild's equations work at all scales, then maybe the cosmos is peppered with these tiny marbles, drifting invisibly, swallowing the occasional particle or two. You might have walked through one already today without noticing, though if that were true, your day would have ended rather abruptly, so probably not. You turn the marble in your mental hand, marvelling at its simplicity. No matter what falls in, comets, starlight, your last embarrassing karaoke attempt, the Schwarzschild black hole reduces it all to the same unadorned geometry. In, swallowed, stored. It's like the universe's shredder, humming quietly in the background, feeding every unique page into the same uniform confetti. And yet the nagging question remains, if the confetti is gone, is the information gone too? Or does the sphere hold on to some echo of what it consumed? The scene feels sterile, like an empty museum hall with a single exhibit. No spinning lights, no chaos, just the clean lines of inevitability. You let your mind wander, tracing the equations in the air. That's the Schwarzschild radius. The math says it plainly, yet the meaning is vast. Every massive object has a Schwarzschild radius. For the Sun, it's about 3 kilometers. For you, it's smaller than a proton. Everyone and everything has a secret black hole self just waiting, though thankfully gravity usually isn't so impatient. And as you drowse on the thought, you realize the comedy of it. The universe is basically saying, you're all black holes in waiting. Some of you just need a little compression. It's like cosmic peer pressure. Luckily, the universe doesn't own a trash compactor big enough for Earth, though if it did, you'd get a front row ticket to the shortest ride in history. The marble you've been picturing suddenly begins to spin, and the void around it swirls like cream stirred into coffee. Welcome to the realm of the Kerr black hole, where rotation isn't just a detail, it changes everything. Unlike Schwarzschild's stoic spherical simplicity, a Kerr black hole is a whirling maelstrom, dragging space-time itself into a dizzy spiral. You can almost feel it tugging on your thoughts, like the spin of a carousel that doesn't stop when you want it to. Roy Kerr, a mathematician from New Zealand, cracked the solution in 1963, giving us the exact description of a rotating black hole. Think of it as Schwarzschild's moody younger cousin who discovered caffeine and hasn't stopped spinning since. Instead of one boundary, a Kerr black hole has 2 horizons, an outer event horizon and an inner Cauchy horizon. Between them lies a region that feels like forbidden property, where the laws of physics start to wobble. Historians still argue whether Kerr himself fully grasped the bizarre implications of his math when he first solved it, or if he simply shrugged and said, well, that's what the equations say. What makes the Kerr black hole especially wild is something called frame dragging. Imagine space-time as a giant sheet of molasses. Now imagine stirring it with a cosmic spoon. Anything nearby, planets, ships, even light itself, gets dragged into the spin. It's called the ergosphere, a swollen oval-shaped region outside the event horizon where nothing can stay still. If you were floating here, you'd find yourself spinning whether you liked it or not, the universe's rudest merry-go-round. Here comes the quirky bit. In theory, you could actually steal energy from a rotating black hole. British physicist Roger Penrose proposed the idea in 1969. Drop an object into the ergosphere, split it in 2 and fling part of it into the hole. The other part can escape with more energy than it started with, essentially pickpocketing the black hole's spin. It sounds like science fiction, but it's been tested indirectly. Astrophysicists think certain high-energy jets from black holes may in fact be powered this way. So yes, the universe runs on loopholes. Now, about that inner horizon, the Cauchy horizon. This is where things get murky, even for equations. Inside, cause and effect start to wobble, like a poorly written time travel plot. Some interpretations suggest you could, in principle, pass through and avoid the singularity entirely, even emerge somewhere else. The idea gave rise to daydreams about wormholes, shortcuts through space-time, and black holes as gateways to other universes. Fringe theorists still love to imagine a Kerr black hole as a cosmic subway station, with infinite platforms, each leading to a different timeline. Convenient if you're running late. But physics throws a wet blanket on this fantasy. Most experts believe that real-world instabilities, chaotic ripples, random radiation, would destroy anything trying to sneak past the inner horizon. The wormhole door slams shut before you can step through. Still, historians and physicists alike argue whether this is a certainty or just an assumption based on incomplete knowledge. The math whispers one story, reality may be another. In your mind, the spinning hole becomes a carnival ride in slow motion. The stars outside blur, their light dragged into spirals, while inside you're pulled toward the abyss with no choice but to pirouette. You're not just falling, you're orbiting endlessly as you fall. It's graceful, terrifying, and more than a little exhausting, like the world's deadliest ballet. And here's the joke your sleepy brain can't resist. You've basically become spaghetti on a turntable. Not only are you stretched, but now you're being twirled like some intergalactic chef is preparing a cosmic carbonara. If the Schwarzschild black hole was the shredder, the Kerr black hole is the blender. You're not sure whether to laugh or cry, so you settle for drifting, dizzy and amused, into the spin. The swirling blender of the Kerr black hole steadies, and now you feel a faint tingle, as though the void itself is charged. Welcome to the strange territory of Reissner-Nordström black holes, the ones with electric flare. Unlike the simple Schwarzschild marble or the dizzy Kerr spinner, this variety carries an electric charge, giving it an extra layer of complexity. It's as if the universe took its cosmic sphere and plugged it into a wall socket. The math for this model first appeared in the 1910s and 1920s from Hans Reissner and later Gunnar Nordström. They asked a wild question. What if a black hole could carry not only mass but also electric charge? Their equations showed that the result wouldn't have just one horizon but two, an outer event horizon and an inner one, a bit like Kerr's structure but without the dizzying spin. Historians still argue whether Reissner himself imagined these things as real or simply as mathematical curiosities. After all, an electrically charged black hole sounds as bizarre as a thunderstorm in a vacuum. The fun detail here is that if a black hole were charged, it would interact with its surroundings differently. Particles falling in would feel not only gravity but also electromagnetic push and pull. A proton, for example, might find itself accelerated or repelled, depending on the black hole's charge. In your imagination, you can almost see sparks dancing across the horizon, as though the abyss had been wired with neon. But reality plays spoilsport. In practice, astrophysicists suspect that any significant charge would quickly neutralize. Space is full of plasma, free-floating electrons and protons. If a black hole picked up too much charge, opposite particles would rush in and balance it out, like cosmic accountants making sure the ledger reads zero. So while Reissner-Nordström black holes are mathematically elegant, most experts doubt they exist in the wild. Still, fringe thinkers love to speculate about tiny charged black holes formed in the early universe, zipping around like glowing pinballs. And here's where the quirky debate kicks in. What happens at the inner horizon? The math suggests a region where time and space swap roles again, leading to strange possibilities like wormholes or alternate universes. But other calculations hint that the slightest disturbance, say a photon wandering in, would destabilize the whole thing, creating a chaotic mess instead. Physicists still argue whether these inner horizons are genuine features of reality or just mirages conjured by tidy equations. As you drift closer, you picture yourself being tugged not only downward but also outward, your body buzzing with phantom static. You remember the way old televisions used to hum when you pressed your hand near the screen, that tingling fuzz across your skin. Multiply that by 1 billion, and you've got the mood of a charged black hole. The mental image is equal parts awe and comedy. You're not just cosmic spaghetti anymore, you're electrified spaghetti. Picture yourself glowing faintly, like a human neon sign blinking open at the edge of the universe. Of course, the sign won't be open long because gravity always wins, but at least you'll look stylish on your way in. The Reissner-Nordström black hole is a reminder of how far theoretical physics will go just to ask, what if? Even if nature rarely builds these exotic beasts, their equations teach us how space-time bends, twists, and sometimes shocks. And you? You let the tingling fade into drowsiness, like the static of an old radio between stations, knowing that even the strangest models have something to say about how the universe keeps its secrets. You drift now into a quieter stretch of thought, where the cosmos seems to laugh at its own seriousness. The phrase that echoes here is the no-hair theorem. Physicists coined it with a wink, as though even they realised they needed a little humour to cope with all this cosmic heaviness. The gist is simple. No matter what you throw into a black hole, planets, stars, antique furniture, even your elaborate playlist, it all gets reduced to just 3 numbers: mass, spin, and charge. That's it. Everything else, every detail, every flourish of individuality is shaved away. Black holes apparently are cosmic barbers. The phrase is usually credited to John Wheeler in the 1960s, though like most catchy scientific quips, its origin is debated. Historians still argue whether Wheeler meant it as a playful metaphor or a slightly exasperated observation, but the idea stuck. Black holes have no hair became shorthand for the terrifying simplicity of these objects. They don't keep souvenirs, they don't flaunt their past meals, they're the ultimate minimalists. Picture it. You drop in a sun, a planet, and a library card. To the outside universe, the black hole doesn't wear any of those details. It just grows heavier, that's the mass, might spin faster, that's the angular momentum, and could hold a charge. The unique identities of what went in, gone, or at least hidden. It's like tossing your grandma's handwritten recipe box into a shredder that only outputs weight, 2 pounds. Not exactly a comforting thought, but of course fringe theorists weren't satisfied. In the 1970s and 1980s, physicists began to wonder whether no hair was the full story. Some suggested that black holes might have subtle hair, not lush flowing locks, but faint whispers of information clinging to the horizon. Think peach fuzz rather than a rock star's mane. The details could be encoded in tiny variations of quantum fields around the hole, faint enough to be invisible to most but still present, like graffiti scrawled on the outer wall of infinity. The quirky fact here, there have even been academic conferences with sessions literally titled, "Do Black Holes Have Hair?" Imagine a room full of world-class physicists debating follicle metaphors with a straight face. It's the kind of thing that makes you realise science at its best has a sense of humour. Still, the central paradox remains. If black holes really have no hair, then information truly disappears, and the universe loses track of details forever. If they do have hair, even subtle hair, then maybe nothing is ever lost, just incredibly well disguised. That question set the stage for some of the fiercest debates in modern physics, debates that still haven't been resolved. You picture yourself now as a strand of hair floating near the horizon. You're not dramatic or obvious, just a faint wisp, a whisper that says, "I was here." And the whole, smooth and aloof, doesn't bother to acknowledge you. You're part of it now, shaved clean into the symmetry of space-time. And then, because your drowsy brain refuses to let a metaphor rest, you imagine a cosmic barbershop sign floating over the event horizon. No haircuts beyond this point. Gravity fades. All styles. Maybe black holes don't just ignore individuality, they enforce their own strict dress code. The thought leaves you both amused and unsettled. You realise the no-hair theorem isn't just about astrophysics, it's about identity, memory, the fear of being erased. If the black hole really shaves away everything but mass, spin and charge, then maybe it is the universe's way of asking which parts of you are fundamental and which are just hairstyles in the wind. The smooth, hairless black hole sits there in your imagination like a smug minimalist, until a new problem barges in, one so unsettling it shook physics to its core. It's the infamous information paradox, first stirred up by Stephen Hawking in the 1970s. You float in the dark, hearing the words echo as though whispered by space-time itself. If black holes evaporate, where does the information go? Here's the setup. Hawking discovered that black holes aren't perfectly black after all. Thanks to quantum effects at the horizon, they slowly leak energy in the form of radiation. It's faint, like the tiniest hiss from an old speaker, but it means black holes eventually shrink and vanish. If the hole disappears, what happens to all the details of what fell inside? Are they gone forever? That's where the paradox kicks in. Physics, at least the version we're comfortable with, insists that information cannot be destroyed. It can be scrambled, hidden, copied, and mangled into forms no one recognises, but never erased. Yet black holes seem to do exactly that. To give it a little history, in 1976 Hawking published his argument that black hole evaporation wipes out information completely. This was more than a bold claim, it was heresy. Quantum mechanics says the universe keeps a ledger of every interaction. If Hawking was right, the rules of physics would need rewriting. Some physicists were scandalised, others energised. Historians still argue whether Hawking framed it dramatically on purpose, he had a knack for sparking debates, or whether he genuinely thought he'd uncovered an unavoidable truth. Either way, the paradox was born, and it hasn't let go since. Now the quirky part, the information paradox became so famous that physicists started betting on it. In the late 1990s, Hawking, Kip Thorne and John Preskill made a public wager. Hawking and Thorne said information was lost. Preskill said it wasn't. They even agreed on the stakes. The loser would buy the winner an encyclopedia, a cheeky nod to preserved knowledge. Years later, Hawking conceded, handing Preskill a baseball encyclopedia at a public lecture. Preskill accepted, but joked that the book might not contain all the information. Physicists, it turns out, can roast each other in ways most sitcom writers only dream of. But beneath the humour, the paradox cuts deep. If black holes destroy information, then determinism, the idea that the present arises from the past in a predictable way, crumbles. If they don't destroy information, then where is it hiding and how do we get it back? The debate splinters into camps. Some argue information leaks out with the radiation, others claim it's smeared on the horizon like holographic wallpaper. Still others say our whole understanding of space-time is missing the bigger picture. You imagine yourself listening to the hiss of Hawking radiation, like static on a cosmic radio. Inside that noise, is there a code? A faint message carrying the details of every atom that ever fell into the hole? You want to lean closer, but of course, it's theoretical static. You can't tune it in. You're left with the drowsy sense of trying to hear a song that might not even be playing. And here comes the joke your sleepy mind supplies. What if black holes are just the universe's equivalent of bad librarians? You hand them your life's work, your precious documents, and they shrug, toss them into a shredder, and then evaporate into thin air. Oops, lost the catalogue, they say. Try again in another universe. It's the kind of absurdity that makes you laugh even as you shiver. The information paradox isn't just a technical debate, it's the beating heart of modern theoretical physics. It asks whether the universe itself is forgetful, whether reality cares about your story, or lets it dissolve into static. And as you float in the dark, the question feels less like homework and more like a lullaby in disguise, a reminder that even the brightest minds still drift in uncertainty. You lean closer to that faint static hiss, and suddenly the night around you flickers. It's not silence anymore, but the faint popping of quantum sparks. This is Hawking radiation, the strange glow of black holes that aren't supposed to glow. You picture the edge of the event horizon not as a perfect boundary, but as a restless surface, where space-time is never quite calm. The explanation goes something like this. In quantum physics, empty space is never truly empty. Tiny pairs of particles pop into existence, then quickly annihilate each other, like cosmic fireflies winking on and off. Usually they appear and vanish so fast you wouldn't notice. But near the event horizon, the rules twist. One particle falls in, the other escapes. To an observer outside, it looks as though the black hole is radiating energy. And because energy has mass, the hole ever so slightly shrinks. Slowly, inexorably, black holes evaporate. Stephen Hawking proposed this in 1974, and the world of physics reeled. Here was a man telling us that black holes, those ultimate one-way traps, actually leak. Historians still argue whether Hawking himself fully trusted the idea at first, or whether he braced for ridicule. But the math was solid, and eventually the concept became one of his most famous contributions. In fact, some say it was Hawking radiation that turned black holes from fringe curiosities into stars of both science and pop culture. Of course, detecting Hawking radiation directly remains beyond us. For a stellar mass black hole, the radiation is colder than the cosmic microwave background, the leftover glow of the Big Bang. It's like trying to spot a candle flame in full sunlight. The quirky twist, though, is that people have tried to create black hole analogues in labs, fluid systems, optical traps, even Bose-Einstein condensates, hoping to see Hawking-like radiation in miniature. These tabletop experiments don't confirm cosmic black holes evaporating, but they hint that the underlying physics might really work. It's the closest humans have come to bottling a piece of the abyss, and here's where the paradox you just wrestled with grows teeth. If black holes evaporate completely, then what happens to the information they swallowed? Does it escape encoded in the radiation, or is it lost forever? Physicists are still split. Some argue the radiation is perfectly random, carrying no details at all. Others think subtle correlations hide inside, like faint watermarks in the noise. Hawking himself flipped his position late in life, admitting he thought information does leak out. But exactly how remains one of the greatest puzzles in science. You let yourself imagine listening to Hawking radiation as though it were music. To your sleepy ears, it might sound like white noise, the kind people use to fall asleep. But hidden within could be the histories of stars, planets, and even civilizations. Maybe the background hum you fall asleep to isn't just static, but the universe's grandest mixtape, playing every story ever told in frequencies too subtle to decode. And of course, your mind slips in a joke. What if the black hole's playlist is just your search history? Imagine some alien civilization tuning into Hawking radiation millions of years from now, carefully decoding the faint signal, only to discover your obsession with cat memes, late-night pizza orders, and that one awkward email draft you never sent. The universe might not be malicious, but it definitely has a sense of humour. The flickering pairs of particles wink in and out as you drift. each one a reminder that even emptiness is busy. The black hole shrinks ever so slightly, and you feel time's long patience stretch around you. The cosmos is playing a very slow game, erasing its giants particle by particle, until what once swallowed suns dissolves into nothing but whispers, and you, lulled by the faint crackle, start to wonder if the whispers are not erasure at all but a secret way of remembering. The whispers don't stop. They ripple outward until the entire universe feels like it's trying to lean in close. You realize you've stumbled into the holographic principle, one of the most mind-bending ideas physics has ever handed us. It begins with a deceptively simple thought. Maybe everything you see, the three-dimensional world around you, the stars, the planets, even your own stretched-out spaghetti self, might actually be encoded on a distant two-dimensional surface. Reality, in this view, is a projection, like a cosmic hologram on the back wall of space-time. The seeds of this idea were planted in the 1970s and 1980s, when Jacob Bekenstein argued that the information content of a black hole must be proportional not to its volume but to its surface area. That alone was radical. Historians still argue whether Bekenstein's intuition was inspired genius or just a lucky hunch. He had no experimental evidence, only reasoning from entropy and thermodynamics. But Stephen Hawking's radiation work gave it teeth, and by the 1990s Gerard T. Hooft and Leonard Susskind had formalized the holographic principle. The universe could be a 2D surface, with the illusion of depth emerging from encoded information. You let the thought settle in. Black holes don't hoard secrets in their depths. They may write them across their horizons, as if their skin holds the diary of everything that's fallen in. Every photon, every quark, every awkward teenage haircut is etched there in patterns so subtle we can't yet read them. It's like the world's most secure USB drive, storing information not in its interior, but on its outer shell. And here's the quirky part. The holographic principle doesn't stop with black holes. Some physicists believe the entire universe might work this way. That means you, lying in bed right now, might actually be a 3D projection of information written on the farthest edge of the cosmos. Your room, your pillow, your phone screen, it's all part of the holographic illusion. If you're feeling slightly unreal, that's okay. Technically, according to this idea, you are. Skeptics, of course, are quick to point out that illusion doesn't mean fake. The chair you're sitting on is very real in the sense that if you fall off it, you'll bruise. But at a fundamental level, the information describing that chair may not be inside it, but on some horizon you'll never touch. Physicists still debate whether the holographic principle is a literal truth or just a useful metaphor, a placeholder until something deeper comes along. The argument continues, often in papers with grand titles but enough equations to make you wish for a nap. You close your eyes and picture your world as if it were etched on glass, every detail flattened into shimmering patterns, and yet when you look at it from the right angle, the illusion of depth returns. You're both flat and full at once. You are the projection, and you are the projector. And because your mind can't resist comedy, you imagine discovering a sticker on the back of the universe. Made in 2D, do not fold, spindle, or mutilate. Maybe reality itself comes with fine print. The holographic whispers linger, soothing in their absurdity. Instead of erasing, maybe black holes archive. Instead of destroying, maybe they compress, storing the past in ways we haven't learned to read yet. You let the thought tuck itself around you like a blanket. Whether or not you're flat, whether or not reality is projected, the idea is strangely comforting. Somewhere out there, on some horizon, every story is still written. You let that holographic blanket wrap tighter, but just as you're getting cozy, a new argument intrudes, one that feels less like a lullaby and more like a fire alarm. Physicists call it the firewall paradox, and it asks a brutal question. What actually happens when you fall into a black hole? Do you slip peacefully across the horizon, barely noticing the transition, or do you slam headfirst into a blazing wall of high-energy particles that roasts you instantly? Sweet dreams, right? Here's the setup. According to general relativity, nothing special should happen at the horizon. If the black hole is huge enough, you might not even feel the crossing, at least not until tidal forces pull you apart deeper in. This idea is nicknamed the no-drama scenario, but in 2012, a group of theorists, Almeri, Marolf, Polchinski, and Sully, often abbreviated AMPS, threw a Molotov cocktail into the debate. They argued that if information really escapes through Hawking radiation, then the horizon itself can't be smooth. Instead, it must bristle with violent quantum excitations, a so-called firewall. And so much for no drama. Historians still argue whether the AMPS paper was intended as a literal claim or a thought experiment meant to expose flaws in our assumptions. Either way, it lit physics discussions on fire, pun absolutely intended. The idea of a firewall violated Einstein's cherished principle of equivalence, which says you shouldn't be able to tell whether you're falling freely or just floating in space. If firewalls are real, then relativity itself takes a punch to the jaw. Of course, other physicists weren't having it. Some proposed that the paradox could be resolved with new twists on the holographic principle, or with subtle entanglement patterns between radiation and the horizon. Others claimed firewalls are illusions conjured by oversimplified math. The debate rages on. Every year, new papers appear with titles that might as well read, "Firewalls, do they exist, or are we just tired?" And then there's the quirky angle. A few fringe thinkers argue that if firewalls exist, they might only appear for certain kinds of observers. In other words, whether you fry or float could depend on your perspective. From one point of view, you glide smoothly through. From another, you burn instantly. Both experiences are true, but they can't be reconciled. It's the cosmic equivalent of being told your dinner is both piping hot and frozen solid. Good luck chewing that paradox. You imagine yourself now at the edge of the horizon, debating your options. Do you trust Einstein and go for the calm crossing, or do you brace for a barbecue? The thought is unsettling, but also faintly ridiculous. You can almost picture a sign hanging at the edge, "Welcome to the event horizon. Warning, contents may be hot." Maybe the black hole is just a cosmic fast food chain with very strict health and safety disclaimers. As you drowse deeper into the imagery, you realize the paradox is less about flames and more about what it says of reality. If firewalls are real, then the universe isn't as smooth and gentle as we hoped. If they aren't, then we're still missing some crucial piece of the puzzle. Either way, the black hole horizon remains a mystery doorway, guarded not by certainty but by debate. You let the uncertainty roll over you like warm air, not flames but the suggestion of them, lulling rather than scalding. Whether it's soft horizon or raging firewall, you know you won't feel it here, drifting in thought. The universe might burn or it might cradle, but tonight it simply hums. The hum around you softens into something almost domestic, like the rustle of pages in a library, and that's exactly where your mind wanders now. Black holes as cosmic librarians. Instead of fiery ends or bald minimalism, you picture them as vast, silent archives, each one collecting the history of everything that has ever fallen inside. It's not a shredder, not a blender, but a filing system so strange that we can't yet read its catalogue. The idea sneaks back to Bekenstein again. In the 1970s, he argued that the entropy of a black hole, the measure of its hidden information, was proportional to its horizon area. Not the volume inside, but the surface. That suggestion cracked open the door to imagining black holes not as destroyers, but as record keepers. Historians still argue whether Bekenstein was taken seriously at first. After all, entropy and black holes sound like an odd couple. But when Hawking radiation joined the party, suddenly entropy became unavoidable, and the librarian metaphor began to feel less fanciful. You let yourself drift into one of these imagined libraries. The shelves stretch outward in impossible directions, curving with space-time, endless yet finite, like a dream where you keep turning corners and finding more corridors. Every book is a story of something that fell in, a star, a planet, a bottle cap from a forgotten space probe. Even light has a volume here, written as a chapter in the Library of the Abyss. The quirky tidbit? Some physicists have even proposed literal black hole computers. If black holes really store information on their horizons, then in theory they could function as the densest hard drives in the universe. A single black hole might hold more data than all the human-made storage devices combined. Of course, you'd have to get close enough to read it, which is a little like saying, "This flash drive contains everything you'll ever need. Please insert your entire body into a star's death spiral to access." Still, you can't resist the image of astronauts floating up to a black hole with library cards in hand. At the door, a stern librarian hologram might greet them. "Quiet, please. Eternity is reading, and if you break the rules, perhaps you're shushed with a gravitational wave." Yet the seriousness creeps back. If black holes are libraries, then they're ones we can't yet enter. Their catalogues may be perfectly ordered, but the doors are locked from the inside. Scholars still argue whether the books are preserved intact, or whether the information is scrambled beyond recognition. Maybe the data is there but encoded in a language so alien it might as well be gone. You run your hand along the phantom shelves, feeling the weight of centuries and galaxies pressing against the bindings. Somewhere in here might be the full script of the universe, every comet's path, every heartbeat, every word ever spoken. Somewhere in here might be your own life, compressed into equations, filed away as neatly as a library slip. And then the joke arrives, soft and sleepy. What if black holes charge late fees? Imagine the bill that would rack up after billions of years. You'd owe so much the library would have to collapse into another black hole just to keep the receipts. The humour fades into a hush. The library of the cosmos doesn't raise its voice, doesn't hurry, doesn't forget. It waits, quiet and patient, even as the universe outside keeps changing, and you, drifting drowsily in its stacks, realise that whether or not the catalogue is readable, the thought itself is soothing. Nothing is lost. Every story remains. You wander deeper into the library's endless shelves, and suddenly the books seem less like paper and more like vibrating strings, humming softly as though they are alive. This is where string theory unfurls its possibilities, trying to explain how black holes might truly store information. You imagine the quiet stacks transforming into tangled webs of filaments, each string vibrating at its own pitch, composing the symphony of the cosmos. String theory suggests that at the tiniest scales, particles aren't dots but loops or strands, each mode of vibration giving rise to mass, charge, and spin. If that's true, then maybe black holes don't destroy strings at all. They weave them into complex tapestries across their horizons. The hair you once thought was absent might instead be these faint entangled patterns, storing every detail in a way we can't yet decipher. Historically, string theory caught fire in the 1980s and 1990s as physicists hunted for a theory of everything. It promised to merge quantum mechanics with relativity, two frameworks that normally glare at each other like rival siblings. Black holes became one of string theory's testing grounds. Historians still argue whether the field blossomed because of its explanatory power or because it was simply the best game in town. Either way, it gave scientists new tools to think about how black holes archive the universe. One quirky breakthrough came in the mid-1990s when Andrew Strominger and Qumran Vafa used string theory to calculate the entropy of a certain kind of black hole. They treated it as a pile of strings and brains, higher dimensional sheets, and counted the possible configurations. Amazingly, their number matched Bekenstein's prediction about black hole entropy. It was as though someone had cracked open the library's door and shown that the books really were there, even if we couldn't read them yet. Of course, not everyone is convinced. String theory has been criticised for its lack of direct experimental evidence. To some, it feels more like an elaborate dream than a tested reality. Still, in the context of black holes, it offers one of the clearest hints that information isn't destroyed, it's just rewritten into the language of strings. You picture the black hole horizon now as a woven net, shimmering with threads that stretch across dimensions you can't see. Every object that falls in doesn't vanish, it becomes a new stitch in the fabric. Your own story is there too, encoded in vibrations, folded into loops, part of the song the strings are always humming. And because your drowsy brain insists on mischief, you imagine those strings forming a literal harp. The black hole plucks its horizon like an instrument, playing a lullaby in frequencies no human ear can hear. Somewhere out there, maybe the universe is nodding off to its own bedtime music. Whether or not string theory is right, the image soothes you. The cosmos may be complicated, tangled, even unprovable, but it also hums with structure. You sink into the vibration, the gentle certainty that nothing truly disappears. Every thread, every note, every memory is still part of the great weave, stretched across the surface of the abyss. The hum of strings fades, and in its place rises a stage, half theatre, half laboratory, where two very different plays are performed at once. This is the realm of the ADS/CFT correspondence, one of the most celebrated ideas in modern theoretical physics. It's a mouthful, yes, but the dream it carries is simple. A universe with gravity might be exactly equivalent to a universe without gravity, written on a lower dimensional surface. You're essentially watching a cosmic magic trick where the same story is told two ways, one in 3D, one in 2D, and they always match. The idea first took shape in the late 1990s when Juan Maldacena published a paper that would change how physicists thought about black holes. He proposed that a type of space called anti-de Sitter space, ADS, with gravity could be mathematically equivalent to a conformal field theory, CFT, on its boundary, a space with one fewer dimension and no gravity at all. Historians still argue whether Maldacena realised at that moment just how seismic his idea would be, or if he thought of it as just another clever tool. Either way, the correspondence sparked a revolution, and conferences haven't stopped buzzing since. In your drifting imagination, you see a black hole sitting inside the ADS bulk, while on the boundary, a kind of holographic screen, the story is written in flat equations of quantum fields. Everything that happens inside has an echo outside. Throw a particle into the black hole, and the CFT registers it as a subtle change in its state. It's like watching a play from two perspectives, backstage, with props and actors and chaos, and from the audience, where it all looks seamless and polished. The quirky detail: physicists sometimes describe the boundary CFT as a shadow theatre. Imagine ancient performers casting silhouettes on a wall by candlelight. The shadows look like their own world, complete with drama and structure, yet every twitch of the shadow comes from something happening behind the curtain. If the ADS/CFT principle is real, then our universe might be the ultimate shadow play, acted out by equations we can't quite see. For black holes, this correspondence is tantalizing. It suggests that all the information about what falls into a black hole could be fully captured by the boundary theory. Nothing is lost, it's just rewritten into another language. If true, then the information paradox dissolves like morning fog. The black hole doesn't erase, it translates. Of course, skeptics point out that our universe doesn't look like anti-de Sitter space. It appears more like de Sitter space, with positive curvature thanks to dark energy. Whether ADS/CFT applies directly to our cosmos is still hotly debated. Some researchers argue it's just a toy model, brilliant but limited. Others believe it hints at a deeper principle, one that might someday encompass all universes, including ours. You sit in the imaginary theatre, watching both plays at once, the actors backstage sweating under the lights, and the shadows dancing elegantly on the wall. You realise you're both audiences at the same time, both truths coexisting, and then, because your mind craves levity, you imagine physicists at a literal shadow puppet show, squinting at the wall and muttering, "Clearly this correlates with a higher dimensional gauge theory." Maybe the universe isn't laughing at us, it's just letting us enjoy the world's most elaborate puppet performance before bed. The stage dims and the shadows soften. The correspondence whispers its message. Maybe everything has two faces, two languages, two ways of being true. And maybe the black hole isn't a grave but a translator, quietly converting reality into a script we haven't yet learned to read. The theatre fades, and suddenly you find yourself not in deep space but in a laboratory, surrounded by polished mirrors, lasers, and oddly humming equipment. Welcome to the strange frontier of simulated black holes on Earth. Since we can't exactly hop in a spaceship and drop instruments into a real event horizon, physicists have gotten creative. They've started building analog black holes, systems here on Earth that mimic the physics of horizons, allowing us to glimpse how information and radiation might behave. One of the earliest playgrounds for this came from fluids. In the 1980s, Canadian physicist William Unruh suggested that sound waves in a moving fluid could experience something like an event horizon, if the flow speed exceeded the speed of sound. In such a setup, sound inside the horizon couldn't escape upstream, just as light can't escape a black hole. Historians still argue whether Unruh's thought experiment was meant to be practical or just a clever metaphor. Either way, decades later, people actually built versions of it, using water tanks, optical fibres, and even ultra-cold atoms. The quirky twist is that some of these experiments have reported faint signals reminiscent of Hawking radiation. Not the real deal, no one is bottling actual black holes in the lab, but mathematical analogues. For example, in Bose-Einstein condensates, researchers have observed particle pairs forming at horizons in ways that mirror Hawking's predictions. It's like listening to a cover band. You're not hearing the Beatles, but the melody is unmistakably familiar. Of course, critics point out that analog systems aren't perfect. The physics of fluids or light doesn't capture everything about gravity. Some skeptics say these setups are little more than fancy toys, but for others they're invaluable. offering glimpses into phenomena otherwise impossible to study. Historians still argue whether the first confirmed analog Hawking radiation was a true milestone or just experimental optimism dressed up as breakthrough. You imagine standing beside one of these lab horizons. Instead of swirling stars and cosmic silence, you hear the whir of machinery and the soft beep of monitors. Instead of falling toward infinity, you're watching ripples in water or flashes in fiber optics. And yet, the principle is the same: horizons, particles, radiation. The abyss recreated in miniature. The image grows playful. What if scientists actually did build a full-scale black hole in the lab? Picture a group of grad students carrying a sign, "Do not feed the black hole." Someone would inevitably try to toss in a sandwich just to see if it stretched. It's the kind of thought that reminds you human curiosity is both brilliant and slightly reckless. But there's comfort in the idea too. By building these analogues, we're proving that even the most alien features of the cosmos can be nudged into our human-scale world. We can't travel to the real abyss, but we can coax its echoes to appear in water tanks and laser beams. The library of the universe, it seems, is willing to lend us practice copies, little paperbacks of the grand tomes stored in the stars. You lean closer to the lab horizon, listening to the faint hum. It doesn't sound like destruction. It sounds like curiosity itself, buzzing, probing, always asking what secrets the abyss might share. And in that steady hum, you hear a lullaby of human persistence, a reminder that even in the face of cosmic darkness, people keep building lamps. The laboratory hum fades, and suddenly you're gliding across galaxies, swooping toward the glowing heart of a spiral. At the center, you find it, a supermassive black hole, millions or even billions of times heavier than our sun. These aren't the pebble-sized relics of stars you've imagined so far. These are giants, sitting like anchors in the cores of galaxies, and every galaxy we've checked seems to have one. They're less like cosmic accidents and more like permanent fixtures shaping the dance of stars around them. The most famous of these, Sagittarius A star, lurks in the middle of our own Milky Way. For decades, astronomers watched stars whip around an invisible point, some moving faster than a bullet. The only explanation was a monster, about 4 million solar masses compressed into a region smaller than Mercury's orbit. In 2022, humanity got its first blurry portrait of Sagittarius A star thanks to the Event Horizon Telescope, a planet-sized network of radio dishes. Historians still argue whether those pictures are more art than science, but either way the images felt like peeking into the abyss with human eyes for the first time. Quirky detail. In 1974, long before the telescope snapshots, astronomers Bruce Ballack and Robert Brown detected a strong radio source in the galactic center. Brown jokingly dubbed it Sagittarius A star, with the asterisk meaning exciting, and the name stuck. Imagine if all scientific names had that kind of casual flair. Black hole, but spicy addition. Supermassive black holes aren't quiet either. When actively feeding, they become quasars, blazing beacons visible across billions of light years. Gas spirals in, heats up, and shines so brightly that the quasar outshines the galaxy around it. In those moments, the black hole isn't just a storage vault, it's a lighthouse, a roaring engine fueled by gravity itself. You drift closer and imagine that these giants are galactic memory banks. Every star, every cloud of gas, every unlucky comet that falls in becomes part of the archive. If stellar black holes are pocket notebooks, then supermassive black holes are encyclopedias, storing the epics of entire galaxies. The histories of billions of worlds could be pressed into their horizons, waiting in silence. Of course, there's debate about how these giants form. Did they start as smaller black holes that merged and merged again, like stacking cosmic Lego blocks? Or did they form directly from collapsing clouds of primordial gas in the early universe? Historians still argue, and the truth may be some messy combination of both. The mystery lingers, humming at the edges of every galaxy. You let yourself float above Sagittarius A star, imagining the encoded stories of our own galaxy within its skin. Somewhere in there might be the record of Earth, the dinosaurs stomping, the first humans lighting fires, you scrolling late at night when you swore you'd go to bed earlier. It's all there, woven into the surface of the cosmic archive. And then your sleepy mind slips in a joke. If these are galactic memory banks, do they also charge overdraft fees? Maybe the reason galaxies collide so often is just because they're black holes are merging accounts. Somewhere out there, a cosmic banker is sighing over the paperwork. The humour fades into quiet awe. Supermassive black holes aren't just monsters, they're historians. They sit patiently, swallowing, storing, never blinking. As you drift in their orbit, you feel less like prey and more like part of the record. A tiny note in a galactic ledger that never closes. The galactic ledger fades and you find yourself staring at something even stranger than a black hole. Instead of pulling matter in, this thing seems to spit it out. Welcome to the speculative world of white holes, the theoretical mirror images of their darker cousins. If a black hole is a one-way door inward, then a white hole is a one-way fountain outward. Nothing can enter, only leave. You watch the idea unfold like a film running in reverse. Stars, gas, even light spraying outward as if the universe itself pressed rewind. The concept dates back to the 1960s, when mathematicians studying Einstein's equations realized that if you time-reversed a black hole solution, you'd get a white hole. Historians still argue whether these were ever meant to be physical possibilities or just mathematical curiosities. Pretty, but impractical. To date, no one has ever spotted one. If they exist, they might be fleeting, unstable, or tucked away in regions of space-time we can't see. Here's the quirky twist. Some theorists have suggested that what we think of as the Big Bang could itself have been a white hole, the ultimate outburst, ejecting everything in one singular explosion of information. In that picture, every galaxy, every star, and even you are the spray from a cosmic fountainhead. Not everyone buys it, but the thought is dizzying enough to keep you awake an extra minute before sleep finally drags you under. Others speculate that black holes and white holes might come as pairs, linked like cosmic siblings. Matter falls into a black hole here, only to be ejected through a white hole somewhere else, or someone else. That's the seed of many wormhole fantasies, the dream of shortcuts through space-time. Fringe papers have even argued that miniature white holes might pop up as the end state of evaporating black holes. Instead of fading quietly into nothing, they could cough out everything they'd swallowed in one final gasp, like a librarian dumping their entire archive onto the floor. You drift through the image of a white hole spraying stars, and it feels less destructive and more like fireworks. Bright, celebratory, fleeting. Maybe the cosmos isn't just hoarding, maybe it's recycling, returning what was swallowed in a new form. And then, because your sleepy brain insists on playfulness, you imagine a cosmic prankster replacing black hole, warning signs with white hole signs. Caution, objects may eject without warning. A universe with exit doors instead of entrances sounds chaotic, sure, but also oddly hospitable. The truth, though, is that white holes remain hypothetical. They may never exist outside of equations. Still, they serve a purpose. They remind us that every theory has a mirror, every story a counter-story. And whether or not fountains of light actually burst somewhere in space-time, the thought is soothing, because it whispers that nothing is final, not even the abyss. The fountain of the white hole dims, and you find yourself circling back to the question that started it all. If black holes really do store the history of everything, could we ever retrieve it? You hover at the edge of the abyss like someone staring at a locked safe, wondering if the combination is hidden in plain sight. The shelves are there, the files are there, at least according to the theories, but can anyone check them out? Physicists have toyed with retrieval schemes that sound equal parts ingenious and absurd. One idea suggests that Hawking radiation isn't purely random. If you study it closely enough, correlations could reveal the lost information. It's like listening to static on the radio and realizing there's a faint Morse code pattern inside. In principle, the information could all be there, just so scrambled that untangling it would take longer than the lifetime of the universe, which is not exactly a friendly user interface. Historically, the dream of black hole decoding has drawn some of the biggest names in physics. In the 1990s, Leonard Susskind and Gerard 't Hooft argued that information must be preserved, sparking the famous black hole war with Hawking. Historians still argue whether this feud was mostly professional or partly playful. Susskind later admitted that while they disagreed fiercely, Hawking's stubbornness sharpened everyone's thinking. In the end, Hawking conceded, but the practical matter of how to get information back remains unsettled. Here's the quirky part. Some researchers have proposed firing entangled particles into a black hole and using quantum tricks to pull correlations out of the radiation. Others imagine ultra-advanced civilizations harnessing the black hole's spin, draining energy and extracting subtle signals. And then there's the boldest speculation. that future physics might allow us to treat black holes as literal computers, running calculations and outputting results in their radiation patterns. Imagine applying for a grant to use Sagittarius A* as a quantum processor. Good luck with the ethics review, but the obstacles are enormous. The radiation is faint, the timescales immense, the decoding algorithms unimaginably complex. It's as though the universe has encrypted its diary with a key hidden across eons. Physicists still debate whether this is a practical impossibility or just a technical challenge waiting for the right breakthrough. You lean closer to the horizon in your mind, trying to listen for patterns in the static. What if you could catch the faintest echo of a star that fell in millions of years ago? Or the exact trajectory of a comet that once brushed Earth's skies? What if, hidden in the hiss, was the story of your own life, perfectly preserved? The thought is both exhilarating and exhausting. And then your drowsy humour kicks in. Imagine black holes as cosmic customer service reps. You call in, "Yes, I'd like to retrieve my childhood memories, please." And the abyss answers, "Your estimated wait time is 14 trillion years. Please hold the hold music, of course," would be Hawking radiation's hiss. As the joke fades, the reality remains. Maybe retrieval is impossible. Maybe the information is there but forever beyond our reach. Or maybe one day someone will crack the code, and the black holes will open their archives. Until then, they remain silent librarians, keeping the stories safe, whether or not we ever get to read them again. You drift now toward the final abyss, and instead of fear, you feel a strange calm, as though the darkness isn't an ending but a book gently closing. All the arguments, paradoxes, and equations swirl together into a single idea. History folded into darkness. Black holes may not be destroyers after all. They might be the universe's ink, writing everything into the deep pages of space-time. You recall the first collapse of stars, the neat spheres of Schwarzschild, the dizzy spins of Kerr, the charged curiosities of Reissner-Nordstrom. You remember the no-hair joke and the information paradox that dared to accuse the cosmos of forgetfulness. You've listened to Hawking's hiss, peered into holographic whispers, debated firewalls, and wandered the quiet stacks of cosmic libraries. You've touched vibrating strings, watched shadow plays in ADS/CFT, peeked into laboratory horizons, and drifted across galactic memory banks. You even toyed with fountains of white holes and puzzled over how anyone might read the archives. And through it all, one thought kept surfacing. Nothing is truly lost. Historians still argue whether black holes are vaults or shredders, whether they preserve or erase. But maybe the truth is more poetic. Perhaps the very act of falling into a black hole is itself a form of preservation. The details don't vanish. They're folded, encrypted, compressed until they're no longer recognizable to us. Like pressing flowers in a book, you can't see the bloom in full, but the imprint remains. The quirky speculation that lingers is this: maybe one day far in the future, when the universe is older and stranger, someone will crack the code. They'll hold the hiss of Hawking radiation up to their ear like a seashell and hear not static but stories, galaxies forming, civilizations rising and fading, your laughter on some ordinary afternoon. Maybe the black holes are patient storytellers, waiting for an audience with enough time to listen. You float at the edge of the cosmic page, and the black hole before you is no longer frightening. It's a librarian, a musician, a shadow theatre, a vault. It's the universe keeping its receipts, refusing to let anything slip entirely into nothingness. The darkness is not silence but storage. And then, with a sleepy grin, you imagine the universe itself as one giant black hole, storing its entire history in layers of horizons. Maybe this bedtime story you've been following isn't just a story, it's already written, folded into the dark, waiting to be reread. So you let the darkness take you, not as an ending, but as a cradle. Every detail of you, every thought tonight, every drifting laugh. It's all history, and history has a home. The abyss is the archive, and you're already inside its pages. And now, let the story itself fade, like stars dimming behind heavy clouds. The grand debates, the equations, the jokes about cosmic librarians, they can rest quietly in the back of your mind. The pace slows, the images soften, and all that remains is the feeling of drifting deeper, as though gravity itself has taken on the role of lullaby. You picture yourself lying at the edge of a horizon, not stretching, not burning, just floating. The pull is gentle here, steady as a tide, rocking you back and forth until your body forgets the difference between falling and sleeping. Every sound you hear in your room, the hum of a fan, the tick of a clock, the faint creak of the walls, merges with the imagined hiss of Hawking radiation, a background static that soothes instead of unsettles. The universe feels less like a puzzle now and more like a blanket. Every detail, every worry, every tiny flicker of your day is folded into its fabric, pressed gently into the darkness where it no longer weighs on you. The questions remain unsolved, but you don't need the answers tonight. It's enough to know that the cosmos keeps its receipts, that nothing is lost, not even you. Your breath deepens, matching the slow rhythm of orbiting stars. Your body loosens, no longer clinging to the day's gravity. You're stardust in the archive, a story written into the horizon, preserved in a page of the universe's endless book. So close your eyes, let the darkness turn gentle, and trust that every part of you, every laugh, every thought, every dream, is already stored safely in the cosmos. Sleep comes quietly, carrying you across the horizon,